So we are talking about so we are talking about off-road dipole. What is an what is an off-road dipole? Then we can finally move to off-road dipole. There we'll see how an actual antenna produces the radiation pattern. We'll study why its length approximately a lambda by 2, what the current distribution looks like, why radiation is maximum for outside, why radiation is nearly zero along the antenna axis, radiation pattern, radiation resistance, flame directivity, why is it effective from the antenna. So suggest out immediate next step. Okay. First we are looking at half-wave dipole. Right. Do I use it in a to cover point vector so negative overflow. So let's start half-wave dipole. Uh, Before that, we will understand what is the internal structure of a half-wave dipole. The dipole itself, a half-wave dipole is simply two separate connecting pieces, top arm, bottom arm, and small gap. There is an electrical gap at the center. The two arms are not electrically connected to each other. So they are not electrically connected to each other. There is gap. Then does the signal come from? We need to connect the RF source to those two arms. That's what feeding you the antenna means. Imagine a signal source, top arm and RF source. Right? Okay. Then where does the signal come from? We need to connect the RF source to those two arms. That's what feeding the antenna means. Imagine a signal source. The source applies a voltage between the two arms. So when I say the dipole is above the center, I mean the RF source or the transmission line supplies. So RF source and transmission line are both same. Supply the signal across the gap between the two arms. So the RF source comes, a transmission line comes here, and the feed is connected top to the bottom, separately inner and outer conductors. Where does the transmission line come in? Suppose we are using a coil variable to derive the RF signal. The coaxial cable has inner and outer conductors like this coaxial cable inner and outer conductor of steel. At the antenna center, the coax is connected to two dipole arms, conceptually inner conductor or outer conductor bottom. Why do we need two arms? We are equal to enough for omega t because an RF voltage is an outlet between 2 points. The force makes one arm relatively positive while the other is relatively negative, and the positive polarity reverses to the current alternative top and bottom arm. So force in half the cycle later the direction reverses. This creates the alternating current distribution that produces radiation. It does not mean current is simple entering from the top and exiting the bottom. This another combination as when you see the antenna is amplified. It means the source is connected at the center. It does not mean source, top, bottom, source like flowing through pipe. It is the RF source establishes a time varying voltage and current distribution from the forms. Now our hybrid dipole picture becomes much cleaner. Top and bottom RF source here. The center is the field point where total conducting and is approximately lambda beta, so we charge is approximately lambda by 4 on deflection correction when discussing an internet linear field point where the source setting transmission and carrying RF energy to the antenna. Antenna is the term. So RF source is not always transmission. This is new to me. Exactly, RF source and transmission are two different things. So the distinction is important in antenna theory. Think of whole system as three separate things. RF source creates RF signal. Transmitter carries RF energy. Antenna radiates RF into space. RF source generates high frequency electrical signal. For example, imagine a transmitter generating. This is the electrical signal all the time. The source could be part of the transmitter spectrum containing oscillators. Okay. Transmission line carries RF. Okay. Antenna, RF, electrical RF antenna, RF electrical energy and produce electromagnetic radiation. Our mobile phone generates RF. Okay. Our mobile phone also generates a radio wave. When we call somebody, that also is it as a radio wave frequency. Yes, your mobile phone generate electromagnetic data. Radar frequency pass out of searching when it continues. Radio aren't exactly thinking. The RF radio frequency refers to the electromagnetic waves used for radio or wireless communication. Mobile phone thinking. Okay, means this will done by the antenna itself. Transmitter antenna itself will do the RF and sorry, transmitter antenna. The mobile towers you see will collect the radio waves and convert into electrical RF signals, and then the transmission path to antenna and antenna to RF electromagnetic wave, antenna to RF. So that's what happens. So continue after the. As the tariff source speed antenna variation is here, we can continue the after dipole property. First, look at the complete dipole top arm. This is bottom up, this is current, this is gap, feed, or fuel point. The total length approximately L equals to lambda by 2. So each of the approximately lambda by 4. What actually happens when RF is applied? Suppose the RF is producing an alternating voltage. During one part of the cycle, the current flows like this. Here, bottom, the current flows like this. Then the half of cycle, the current reverses. That means charges in the antenna are accelerating, therefore accelerating charges feels more open. So the current is not the same area, which is extremely important. You might initially imagine with the same current engineer, that's not what happens. Because the antenna has a finite length, it travels around the conductor and reflects the openings at one end. I equals to 0, therefore current distribution becomes approximately 3 meter per half wave. Equals to 0 and more than equals to M at the center. Why does the center have maximum current? Because the center is where the RF source is connected. The source drives the current into two arms. As we move toward the either end, the current must eventually reduce to zero because the end is open, so the current distribution naturally looks approximately like a sine wave, like a half sine wave. This is one reason of the length of approximately lambda naught is special. Now comes radiation. What he is saying is, I'm reading it in a not that understanding. Here, current flows in opposite direction. Uh, this is top arm, this bottom suppose transmission line is connected to source, feed point, and this outer conductor, inner conductor, and outer conductor. Current is entering. This is a closed path. You see this, but our not DC source. It's an AC source. So when this is changing current, you see first cycle this happens, second AC cycle this happens. Due to this alternating back and forth happens, accelerating charges produce a radiation field, but the current is not the same everywhere. So current is not same. This is extreme important. You might initially imagine it is fuel current area. That's not what I mean. Because the antenna has a finite length, wave travel along the conductor and reflect at the openings. So at the openings it will reflect. At the opening I equals to 0, opening side current is 0. Therefore, so this is the current graph and this is the maximum graph. The current enters becomes 0 and becomes maximum here and again becomes 0. This is the cycle happens in a half wave dipole AC radio signal. Current current will become 0, current will become max, current will become 0. I equals to 0 at both ends. I equals to I max at the center. So I max at the center. Because the center is where the RF source is connected, so drive the current into two arms as we move toward the their ends. The current must eventually reduce to either end. As we move to our either end, the current must eventually reduce to zero because the end is open. So the current distribution naturally looks approximately like a half sine wave. This is one reason a length of approximately lambda by 2 special. So why do we use the lambda by 2? The manufacturer itself doesn't fit the reason we use lambda by 2 is um, because the center is where the RF source is connected, the source drives current into 2 amps. As we move toward either end, the current must eventually reduce to 0. So the current distribution actually looks like a half sine wave. This is the reason approximately lambda by 2. Half sine wave means lambda by 2 whole. Now, we will look it later. Now comes radiation. Every small section of the antenna has changing current, so each section contributes to electromagnetic field. Think of antenna as many tiny radiation sections, tiny current elements. The fields from these sections combine, and this is where the radiation pattern comes from. The road should be radiate eventually in your direction. Depending on the direction, the contribution can add together and partially cancel out. So think of antenna as very tiny radiating. So if we take this horizontal line as antenna, we take a tiny current element from it. The fields from all these sections will combine, and this is where the radiation waves come from. They don't simply radiate equal in all directions. So they will combine here at top or something, uh, and the radiation pattern will come depending on direction. So if the directions of the tiny currents are same, they will add up. If they are not same, then they will cancel up. Uh, why maximum radiation is sideways? Suppose the dipole is vertical, so this is dipole, vertical dipole antenna. Look at the top directly to the side. This is the receiver. The radiation contributes contribution from the. We keep the point directly at the side. This is the receiver. The radiation contributions from the different parts of the antenna combine strongly in the direction in this direction. Therefore, maximum radiation broadside to the dipole. Broadside simply means perpendicular to the antenna. What about the vertical? What about directly above the antenna? Now put the receiver along the antenna axis. So we put the receiver here, then it should be broadside the antenna, like perpendicular to the antenna. But if you put the receiver at the top, what happens? Now put the receiver along the antenna axis. In the in this direction, the contributions from different portions of dipole tend to cancel. So if you put receiver here, in this direction, the contributions of different portions of dipole tend to cancel. Therefore, radiation to zero ideally along the axis. So along the axis, radiation will become zero. So the pattern becomes maximum at sideways. In 3D, the particular that produces the form of donut-shaped radiation pattern. The most important picture so far, think of a half-wave dipole as doing two things simultaneously. Along the way, it is distributing current. Current is maximum at the center, and on the way, it is zero. So, along the way, radiation pattern will be broadside. So, can you say if you are waiting when you say if you I think you mean receiver feedback. You're catching an important terminology now. I said receiver, I meant the actual receiving antenna located somewhere away from the transmitting antenna and not feedback. Okay. We said the actual antenna located somewhere away from the transmitting antenna, not feedback. Let's separate the two antennas. Receiver antenna itself, RF feed line transmit antenna electromagnetic wave, receiving antenna receiver. I call the second antenna location receiver. So when I say put the receiver to the side of the dipole, I mean imagine measuring the radiation produced by the transmitting dipole at the location. It doesn't necessarily mean the second antenna is actually communicating with the first one. Why do we use the imaginary receiver? Here, how much radiation does the transmitting dipole? If we use the imaginary receiver because we want to ask how much radiation does the transmitting dipole send in each direction. For example, receiver if dipole is weak, then move then imaginary receiver silence. If the imaginary receiver silence, it is strong dipole. We're not studying feedback here, we are simply measuring, imagining the electricity at the different points are in the transmitting antenna. So remember, transmitting antenna creates electricity, receiving antenna resists electricity. Receiver position, the limitation with the observing measurement. Why I got the diagnosis? Here you use it two diagrams. So he said the dipole is vertical dipole. Look at the point directly on the side. So he put this is a vertical dipole, he put antenna at the side. The radiation contribution part of the antenna combined strongly in this direction. He is saying we put another antenna at the receiver antenna side. The sideways the antenna contribute a lot. So why does this happen? Means the antenna structure, volume properties and metallic properties all support that. What about directly about the antenna? Now put the receiver along the axis. If you put the antenna here, top of that we at some distance or same distance we put the antenna. Therefore, at the top along the axis, it will be zero. Radiation will be zero. The pattern becomes maximum sideways and radiation. The most important picture so far. Halfway dipole is current distribution in magnet center. Another weak and strong. That's okay. What next? Now we should answer the question we left. Why is the half-wave dipole approximately lambda meter long? And why does the produce current distribution zero max, zero I max equals to zero? This is a fundamental foundation of before we know to this is foundation before we know to radiation pattern and antenna characteristics. Start with wavelength. Suppose the RF signal has frequency of the electromagnetic wave travels to velocity v, so lambda equals v by f in 3 space, lambda equals to c by f. For example, if f equals to 100 megahertz, then lambda equals to 3 into 10 power 8 by 100 into 10 power 6 equals to 3m, therefore half wave dipole would ideally have L equals to lambda by 2 equals to 1.4 meters. Why does the tide train about lunar? Because the RF signal is not instantly present everywhere on the Earth. The electrical signal travels around the conductor. When it reaches the open end, current cannot continue by and by. Therefore, I equals 0 at the open end and wave is reflected. That reflected wave convex the incoming wave. This produces a standing wave pattern. What what Okay, we start with the wavelength. The RF signal has a frequency f. What is the wavelength formula? Uh, where v is velocity, lambda equals to v by f. This is the formula for wavelength. In free space, lambda equals to c by f. In free space, lambda is c by f. For example, if f equals to 100 megahertz, then light speed. C means the speed of light. 3 into 10 power 8 by 100 into 10 power 6. Megahertz means 10 power 6. So micro, mega, and giga. Okay, 3 Therefore, a half-wave dipole would ideally have L equals to lambda naught equals to 1.5 meters. Why does the wire care about wavelength? Because the RF signal is not instantly present everywhere on the wire. The electrical disturbance travels along the conductor. When it reaches the open end, current cannot continue by and by. Therefore, I equals 0. Because the RF signal is not instantly present everywhere on the wire. RF signal is not the wire means antenna. It is not no, the transmission line. Here diagram the transmission line. The electrical disturbance travels along the conductor. When it reaches the open end, current cannot continue beyond the end. Therefore, I equals 0 at the open end. At the open end, I equals 0 becomes 0 because the open end current cannot continue beyond the end. And the RF signal not instantly present everywhere on the wire because here wire means you meant the antenna. I think. Uh, or you can simply right click, ask ChatGPT. Here, wire means female antenna or feed. I think it's feed. Here I said wire, I meant the antenna conducting out, not the field line. So, yeah, two horizontal places on the antenna feed is what applies the RF signal at the center. It's a power cable connected. So he meant the two plates. I call them plates, or you can call them wires because antenna upper wire and lower wire connected. It forms antenna. What is this? So we got lambda by 2 equals to 1.5. Now that the wire size theorem was needed. So we'll discuss the equal given range because the RF signal is not very fastly or instantly going into the wire. Everywhere on the going into the wire. So the wave is reflected. The reflected wave combines with incoming wave. So the wave is reflected. So we know reflected wave, incoming wave, we read in transmission lines, and how the standing wave produces, how the standing wave were formed. This produces standing wave pattern. Imagine one quarter element at the center of the is the feed point. Each arm is lambda by 4 long, uh, lambda 5 by 4. So this side is lambda by 4. This side is open end is lambda by 4. Center to open end, this length is lambda by 4. At the center, I equals to max, at the end, I equals to 0. Therefore, one arm naturally has approximately maximum value. Uh, the other arm does not does the same thing in the opposite direction. Okay. Uh, Here at the center, maximum current will be there, and at the end, zero current will be there. I equals to 0. Therefore, one arm can actually have approximately maximum 0. Uh, it is just the current distribution along that line. Correct. The other arms does the same thing in the opposite direction. That's why you get 0 MMF 0 in the antenna currents. So the entire antenna contains approximately one half of a sinusoidal current wave. It is a current wave. One half of the sinusoidal current wave. Then the total length is L equals lambda by 2. That's why it is called a half-wave dipole. Now an important correction to our MF indication. The center has maximum current because the force is there, that's the useful first institution. But it is in the complete region, the deeper region is the boundary section at the one end plus cross propagation plus reflection, which produces the standing with current distribution. That's the understanding transmission concept of the antenna. Also antenna. What happens if the antenna were shorter? Suppose uh, early is less than lambda, then the current distribution is different and the antenna behaves like a short dipole. If L equals to lambda by 2, we get the classes of the equal lambda by 2. If you make the antenna longer, the other current distributions in antenna is equal. The antenna length is not arbitrary. It is related to the wavelength of the wave trying to transmit the change. You not now understand we have a lambda antenna length, current distribution lambda, so L equals lambda by 2. So we understand why is zero dense and why is max at the center. Why lambda by 2 cube. Lambda means wavelength. The antenna design is the antenna is designed in a way that antenna wavelength. quarter wavelength, half of the wavelength is the total wavelength size, total antenna size. Then half of the two wires, two wire size is lambda by 4, quarter of the wavelength. Now, and it is designed like that. Now, an important correction. Okay. What happens if the antenna were much shorter? Suppose L is less than lambda, then the current distribution is different and antenna behaves like if lambda becomes greater than the length, if the antennas were much shorter than the wavelength, if they designed like that, then the current distribution is different and the antenna behaves like a short dipole. So the antenna's current distribution will be different, not zero, INF zero. It will be something different. We can make antenna longer, other current distribution antenna behavior. So antenna length is not arbitrary. It is related to wavelength of the RF signal we are trying to transmit. Okay, over what's next? Including the radiation may be maximum at 90 0 degrees and so we discuss construction and definition when anti-vector magnetics and separating current distribution, radiation pattern, radiation resistance. We didn't discuss radiation resistance. We didn't discuss directivity or gain. I think have given all this in my LinkedIn page. LinkedIn post I said what is gain and what is directivity, polarization. I have it all. Basic characteristics. Why I forget different those. So radiation pattern is something like for an AC current, uh, the radiation is sideways for a dipole. The radiation, the monopole, like there will be uh, radiation pattern. Okay, we'll look at this later. First, we'll go antenna. Antenna. After dipole, staying within the for equal zero at the ends. Made by the center, what does radiation pattern mean? Suppose our option dipole is putting the place an imaginary receiver and dipole downwards around the field. How strong is the radiation interaction of the radiation? It doesn't mean the antenna produces a different ways. We simply measuring the voltage and the field power in the different directions. With the dipole, typically the antenna axis is vertical. Now imagine our receiver and antenna. There are two important directions along the antenna. So I will cover all this very fast. What is radiation data? So radiation pattern is simply like it has some formula. Based on that, radiations will go Mm, I want to tell, but I forget. Let's continue reducing that even in the forget and activity and the game. Directly is not game, right? With polarization, basic application. I really forget. If you don't realize, you will forget. Our brains are not forget. Let's finish the half-word dipole affection, but keep at the level of a silver treatment. Is giving so much also. How strong is radiation in each direction also is not equal in any direction. Maximum radiation reduces maximum frequency of the antenna, so maximum radiation is theta equals 90 degrees, maximum radiation, theta equals to 0 means 190 zero radiation. So that's it keeps saying pretty much. Why does the pattern have this shape? Because the electromagnetic field produces by different portions of dipole moment differently depending on the direction, some direction depends on the so why does the pattern appear? This is the reason. Directivity. Suppose two antennas receive the same amount of input power. One antenna radiates almost equally in the every direction, and they concentrates mostly of the radiation in the second direction, which is more useful if you want to send energy to a particular location as opposed to the second one. That's the idea of directivity. Directivity is just how strong an antenna concentrates radiation in a particular direction, and isotropic antenna. Isotropic antenna means the reference antenna I talked earlier. Reference antenna means it's like a sphere antenna, sphere radiation. Imagining the ideal antenna where it creates a spherical radiation. It would radiate equally in all directions. Yes, spherical isotropic antenna would radiate in all directions. So a directional antenna concentrates radiation. For an antenna, this is uh, the directivity formula. D equals to maximum radiation intensity, average radiation intensity. So higher D means more directional radiation. The directionality is nothing but how strong the transmitter antenna sends signal towards the receiver antenna, the direction of the signal, like the transmission signal, the directivity, where the directivity is increases or it is a directivity less. Now suppose the two antennas receive the same amount of one antenna radiates almost equally in every direction and that concentrates most of its radiation in second direction. These are two antennas behavior. They are not same antennas. Two antennas where one antenna has a equal in every direction, it has low directivity. So this antenna radiations in certain directions, it has high directivity, which is more useful if we want to send energy toward a particular location. Obviously, the second one. This is the second one is important. That's what we call it high directivity. How strongly antenna concentrates radiation in a particular direction. A particular direction antenna concentrates radiation for an antenna maximum radiation intensity by average radiation intensity. Okay, look into this later. Actually, this is I solved problems on this. Suppose the antennas I solve problems on directivity. Where for antenna we have multiple radiation values. So yeah, I remember the antennas have uh, lobes and nerves. Lobes represent the mm, major lobes, minor lobes. Lobes represent the antenna radiation pattern. Like antenna lobes in antenna radiation. So this is the lobe. Lobe represents the This is the main lobe. Lobe represents the directivity of the radiation pattern. This is a side lobe. This is back lobe. So, the empty places are called null. Uh, okay. This has high directivity. Magnum virus or multiple lobes have different different uh, pattern. Like AC or I think AC current input. Decibels are something we calculate, how we calculate problem exactly. As we are talking about anti-directivity intensity problems where the antenna may radiate different or in different directions, the key is to distinguish power density from duration intensity, radiation intensity. These are formulas. I don't think just uh, okay. We don't go deep. We'll just in the top. For example, do equals to this is gain. Gain is related to directivity. Data is antenna efficiency. Simply directivity, how well does the antenna concentrate radiation? Gain tells us how well does it concentrate radiation after considering the efficiency or losses. Suppose B equals to 10, eta equals to 0.8, then gain is 0.8. So the antenna directivity is 10, but the gain is right because 20% of input power is lost. D is directivity, but gain is right, 20% is lost. This is antenna efficiency. Input is lost. The gain is how much antenna or how well the concentrated radiation considering the effective losses and gains. The gained electromagnetic wave from lost input we lost some input because of the um, directivity because of the antenna. Yeah, polarization. Now, another important characteristics of the electromagnetic waves traveling toward you. The electric field oscillates in a particular direction. The direction in which the electric field oscillates determines polarization. A vertical dipole, this is the antenna. The electric field predominantly vertical, therefore the wing is vertically polarized. When you rotate the dipole horizontally, the electric field becomes predominantly horizontal, therefore horizontal polarization. Where does polarization matter? Suppose the electric antenna is vertically polarized. Yes, the antenna is also vertical. TXRS, a good coupling of first, but if it rotates the receiving antenna 90, TX and RX receive antenna 90. The polarization doesn't match, the receiver signal can become acyclic, therefore TX and RX antenna should have matching polarization. For result communication, basic characteristics of half-wave dipole. For your syllabus, remember this. Then approximately lambda by 2 3 involve center field current network center zero times radiation maximum broadcast radiation axis radial zero PD directivity about 136. But the directivity or gain radiation resistance about 73 ohms for an ideal. One very important distinction, the impedance of every partial dipole. The approximately 73 ohms is only refers to the radiation resistance of ideal Half-wave dipole increase with particular construction thickness where the object of rearrangements can change the actual length of internet. We essentially computed the half-wave dipole contact radiation and direct. I asked the question. I solved the problems from directivity where for antennas we have multiple lobes, we have different AC power, current input, we have calculate for example. No, actually I solved problems like if the relation pattern given the values will be let's say 20. There will be fixed values for each antenna. For a half-wave dipole, it is 100, 20, 20, 20, 0, 0, and 19. Like some values is there. So the directivity is calculated as uh, reference antennas average reference antenna value by uh, maximum. Yeah, I think maximum intensity. Yes, intensity is by average reference antenna antenna in terms of the given antenna value. Yeah. That is different from what I gave you earlier. Yeah. So I understand exactly the problem talking the time of radiation density, where antenna radiation intensity is given at a different angle. So by zero, let's say for 0, 0, 39, 60, 20 degrees intensity, 90 degrees, 20 is 159 and 180. The 20 is the max radiation. Max radiation is 20, but directivity is maximum radiation average radiation intensity. So we need to find the average radiation intensity represented by all these patterns for equally spaced angular samples. The basic idea is essentially the average equals to E1 E2 plus the sum of these and diamond. So we sum of these 20 20. Why he left 0? For example, if your values are this 15 and P equals to 20 by 15 equals to 1.3. That's the maximum intensity by average intensity. But in actual antenna variation pattern problems, the values correspond to angular position. Spherical pattern remain into account of solid angle pointed or writing, so we students blindly take the ordinary average under the problem pattern represents tendency. And I think this is the exact kind of a problem you are handling again. But we solved it differently. We invented then why the ideal antenna value isotropic antenna? We use as reference to calculate directly. It is not that it is a reference antenna. For an isotropic antenna, d equals 1 or d equals 0 degree. Why is it equals to? Suppose your actual antenna has radiation base, you remember tell us how strongly the antenna is in direct different direction. Want to know how much will this antenna concentrate when compared with an antenna that spreads it equally in every direction, that's directivity. So we compare it with isotropic reference. Imagine the actual antenna radiates total power P rad. If the same total power were spread equally in all directions, the isotropic antenna would have average radiation intensity to ISO equals to P rad by 4 pi. But our actual antenna might concentrate more power in a small direction, some direction. At its strongest direction, Umax by also 4 by Umax by this is the now your radiation pattern number 20 Umax by. Then we need to determine the average radiation intensity represented by the interference. The average is objectively the what the esoteric reference would have the same radiated power Umax by U average. This is what your textbook may have solved differently. Mm, let's talk to what's next antenna. Antenna arrays. Actually, antenna is nothing but same kind of antennas pictured in a order like if you put two speakers. What is antenna array? If you put two speakers, the sound waves will get added together and the waves come to us. Same way, the antenna radio waves are antennas, multiple antennas are arranged in a way so their waves will add up and increase directivity to the receiver towards the receiver. So, and more antenna arrays increase directivity. That's what antenna array. Now, yes, now we move to the next explicit topic in our syllabus, antenna arrays. The good thing is that arrays are a natural continuation of the half-wave dipole, which one antenna is present, one antenna means one radiation pattern. Now, what happens? We put multiple antennas together and make them radiate together. That's an antenna array. What I told, that's one radiation pattern, but multiple antennas increase the directivity. What is an antenna array? Antenna array is simply two or more antennas arranged together and operating together. For example, antenna 2, antenna 3. Instead of having an aggregator, we have several antennas are usually arranged in some spacing between them. While with multiple antennas, you might have the one already produced by the Bowen antenna because we can control all the radiation from which antenna to use. Remember what we discussed, use form button. So same direction will add up, opposite direction will get cancelled each other. Now we deliberately creating multiple radiation parameters, space spacing. The simplest array, two antennas, imagine two identical antennas, antenna 1 and antenna 2, these spacing between antennas, both antennas is the antenna the receiver for is the receiver. The wave from the two antennas reach the receiver is the crucial point. The wave can arrive at different phases. Why would those phases be different? Because the distance is traveled by the two waves and the difference of the antenna 1 and antenna 2 towards the receiver. One wave might travel a little further. The path is different to delta and the phase difference is so you can see the antenna 1 it is very close to receiver, antenna 2 it is very slightly far from receiver. Then there is a phase difference. One wave may travel a little further if the path difference is delta r. Then the phase difference caused by the path is del phi. Delta phi equals to 2 pi by lambda or delta r. So the distance difference between becomes phase difference. What happens when the waves meet? Phase from constructive interference. If the waves are in phase, it is wave 1, wave 2 strong. Result, they add up constructive interference, strong radiation. Destructive interference, if they are around 180 degrees out of it. If they arrive in phase, then it is, they will add up. Like, look at this, wave 1 and wave 2 are in same phase. they are all the same way strong. If the array 180 of phase means wave 1 is phase here, wave 2 is 180 degrees, phase difference is there. Therefore, they'll cancel up and weak they cancel district interference weak radiation. This is the entire reason antennas are powerful with one antenna. The radiation pattern is determined largely by the antenna itself. With an array, we can control number of elements, spacing, relative current amplitudes, magnitudes, and therefore control the radiation pattern. So, array interference control or radiation pattern control an important array factor. When studying antenna arrays, you will encounter other factor. Don't be scared by the name. It basically tells us what radiation pattern is produced by the arrangement and excitation of multiple antennas. For an array, we often say total division pattern equals to element pattern into array factor. When studying the antenna arrays, we will find further array factor. So this will be the it basically tells us what radiation pattern is produced by the arrangement and execution of the multiple antennas. The radiation pattern is produced by the arrangement, the excitation of the multiple antennas. So we'll stop here. Uh, take a break. Bye bye. Next video.